Good afternoon. Can you hear me from the back? Ready? Okay. My name is MK Jibi. I'm a technical director at NetApp, and my co-author is Dean Lang, a development architect. What you can see in this paper, we're going to talk about large cluster, the issues that we run into, and how we solve them. Okay. So we're going to show you how coherent model can be employed so that you can have a stable cluster with a good performance at a ultra low latency, and on a low cost storage product. The method that we're going to use, we're going to try to limit accessing, having an optimal I/O, try to access one logical LUN on a single controller with a high speed, and this implied that we're going to use what we call ALUA, the asymmetric logical unit access. Show you some observation that we have on this large cluster that we look at. Whenever you have tolerance access, fault tolerance access, and resilience on a storage product, you can see that in such a way that LUNs are shared among multiple initiator, you can see some difficulty in using ALUA. Okay, we're going to talk about that. We're going to also observe that try to balance IOs, is very hard to do with symmetric active-to-active model, where you have the IO are kind of like spread equally among the storage node. Okay, so each one is trying to hit the array system pretty hard. And then looking at whenever you have a fault, how do you route the IOs? Okay, how do you try to use the ALUA so that you don't end up with time spikes or stalled IO? And then most important is whenever as node increase, each one is trying to determine which one is the optimal path, and each host is going to say, "Oh, fail over," okay, and you'll end up what we call LUN thrashing, and that's what we observed. So what we're going to show you today, we're going to show you a low-cost storage node that uses ALUA in a way that we manage the LUN ownership among these nodes in a very efficient way, and so that we have lean I/O path, while at the same time solving the thrashing problem among large number of nodes. And then, of course, achieve the cache coherence, achieve the performance, do the I/O workload balance among and optimize ALUA nodes. So that is the objective method and result. What would you like to take away from this presentation? We're going to show you how to build a large storage cluster in a heterogeneous environment, where you have different operating systems running at the same time. How we can establish an efficient cache coherency among this large clusters, and what knobs and what tuning parameter you use to establish that, to achieve that. And then, of course, very important that you don't have spike in performance. We're going to show you how we can achieve sustained performance condition, and how to sustain it when we are doing failover between passes and during failback. We'll show how we can sustain that performance. Of course, and doing this at a low latency and lean I/O path, using ALUA in a way that we'll talk about implicit and explicit driver and how they are used. So when you look at a cluster, okay, I show here that few nodes that are heterogeneous so that you have different operating systems running at the same time. They're connected to two redundant switches, and of course, a typical cluster for us can have 64 to 128 nodes, running different operating systems, running different HBAs, running different failover driver, okay, so on and so forth. Now we made it redundant so that each client can access any piece on the storage, any volume on the storage via dual path. So here in this case we have a Linux Dell, we have a Mac, we have The Linux are running an auto HBA, and the Windows also have an HBA driver, HBA host adapter. We have one Brocade switch, and of course I misspelled Cisco switch. I misspelled switch 2. Those have each one has 16 ports. And we have an array system called E5624, array controller from NetApp. That's the pair that E-Series. It's a 24 drive. We configure this into an 8 plus 2 RAID 6. Okay, we configure for 8 volume. Each volume is 14 terabyte. We put it in a dynamic disk pool. This is the mechanism that we have with E-Series to allow us to stripe data across drives. With very low reconstruction rate associated with this mechanism. We use SAS 10K 7200 HDD drives, okay? And we install StorNext because that's what the customer that we're working with has installed. And we installed the new E-Series code, plus we installed an implicit failover driver on the auto HBAs so that we can move the control of path failover from the HBA to the array controller. So the array controller decide when and whether to move a path or not. Why? Because you could have 64 nodes. 2 nodes want this path to be on B instead of A. We're going to look at if 62 want to be on A, we're going to stay on A, all right? So that's something that we'll show you in the paper how we did this. And for that, I'll pass this to Dean Lane.
Okay, can you hear me okay? Everything good? Okay. So Dr. Jibby mentioned that we had implemented an Alua solution, and that's actually been the case for quite a number of years. Of course, Alua is nothing new by any means, right? This is, the concepts have been around 20 years, and the notion of using local caching, and so I kind of want to back up for a second here. Let's talk a little bit about, there's some specifics here of what we've done in the product, but I kind of want to back up to talk about the general approach, and I really want to focus in on that because I think that's what may be useful to everybody more so than specifics of how we did it in the product. But so the concept of Alua, if you're not familiar with it, is the idea that you've got multiple storage nodes in a cluster. In our case, it's just a two node HA pair of storage controllers, and limiting I/O access on a given logical unit to one of those nodes gives you the ability to do local caching. So it's a LUN ownership model. The concept's been around a long time. It's kind of old school, if you will. However, one of the things that we've decided to deal with, use this a little more to actually adapt it and use it going forward at this point, at least as well, is the fact that latency is king now. Everybody wants ultra low latency, and a RAID stack and a storage controller cannot inject a lot of latency into the path. So the fast path through the controller has to be very lean. Using a local caching algorithm that uses Alua or a LUN ownership model actually allows us to have that very lean path. And so because things are focused more on latency, and it's getting more so all the time, we've decided to continue using that model. We've actually used that model for quite a few years. However, and so just to describe what that is, so all the I/O for a given logical unit comes into one controller. The other node, in our case, like I said, it's just a dual pair. The other node does not process any I/O for that logical unit. So if an I/O arrives at a target port on the other node, it is then shipped through an interconnect to the other controller. So obviously there's latency injected by that extra shipping, and you don't really want that. So there are standard methods in SBC for reporting this asymmetric path access, where you have some target ports that produce one level of performance and others that produce a different or lesser performance. And so the initiators can actually take that information that they can query, and they can decide, okay, I'll route all the I/O to the optimal paths. That too is not a new concept. I think that was introduced in the standard probably close to 15 years ago now, somewhere in there. But there's two types of ALUA, implicit and explicit. And explicit ALUA is where the state, so which controller is the optimal controller to own a given logical unit, is controlled by the host. The host makes a decision and makes an explicit decision to actually go in and say, I want this controller to be the optimal path. Whereas implicit, it's the controller making that decision. So it's driven by the other end. And this too, nothing new. Now, one of the difficult parts though, is that when you use ALUA like this, and you get into a clustered situation, a clustered compute situation, where you've got a lot of compute nodes accessing the same logical unit, you have a lot of difficulties because the different initiators can make different decisions on which path they want to use. If you get a fault in the SAN of some kind and you lose connection to, let's say, one host out of 100 loses connection to one of the controllers, it's going to want to start routing I/O to the other controller. Well, that's non-optimal. If the host is making decisions, says, look, I can't see where this is at, I can't see paths to the optimal path, so I'm going to use the other one. I want you to change the optimal paths to this other one. Now all of a sudden the other 90 some odd hosts are fighting it because they want to use the path that it was on. So this whole notion of the host making the decision using explicit ALUA can create thrash in a cluster because the different hosts disagree as to who should own a given volume. So in one hand, we want to use this caching model. We want this simple caching model for a very lean path, I/O path, and we want to use asymmetric access to do that. On the other hand, we're also deploying into more and more clustered compute solutions where there's shared access by a lot of initiators to the same logical unit, and so that's challenging. Okay. So one of the things that's challenging about that is getting the multipath drivers on those compute nodes to play fair with each other. In our case, we deal with a lot of, and the particular tests that Dr. Gibby was talking about, and we'll look at that here in a little bit. In that particular case, we dealt with a lot of different hosts that had different operating systems. We had Linux, we had Mac OS, we had Windows, several flavors of Windows, several flavors of Linux, and all the different drivers and HBAs. And so you get this mix that is kind of a soup of all these different combinations of drivers. They all make different kinds of decisions. They all react differently to different check conditions in different ways. They all like to, they all like to manage paths in different ways. And so the condition you get into is that if they don't play fair with each other in a cluster like this, then you can get into this thrash situation where ownership wants to bounce back and forth between the controllers because the host can't agree. And so explicit ALUA is susceptible to that because the hosts are managing it, like I said. So one of the things we did with our architecture is we use configuration information that the administrator provides and says, okay, these port worldwide names are attached to this host, so these HBAs are in this host, and this is the operating system running on there. And we use that to tailor our behavior on on any responses we send on a particular initiator back to a particular initiator, knowing how that multipath driver typically behaves. For the most part, the drivers most of the host OSs are compliant with the standards, and it all works pretty well, and they all work pretty well together. But there's quirks here and there. So by having this information on what's on the other end of the wire in terms of the OS and the driver, we can kind of get them to play fair together a little better by knowing how they're going to react to certain conditions. The other thing we did was we moved completely to implicit ALUA. So we decide from the storage node which controller should own a given logical unit, so where the optimal path is going to be. Because we have visibility to the entire cluster. We see all of the initiators. We know which ones are connected through which paths, and we can track all kinds of things about them and understand the state of the SAN as a whole and know which one of the controllers is the best owner. And that's really the key thing here, is that by moving to this implicit ALUA model, we can actually make that decision on behalf of the hosts, not have the hosts fight with each other over who should own a given volume. One of the other challenges with ALUA is that it's not like a symmetric active-active kind of environment where all controllers in a storage node or all nodes in a storage cluster have same performance. In that case, if you've got, say, 4 target ports on each controller, and you've got 2 controllers in an HA pair, such as we do, then if all 8 ports have equal performance, the host just round robins across all 8. Load is nicely distributed between all the controllers. With Alua, that's not the case, because all of the load for a given logical unit has to come into one of the controllers. That's one of the serious downsides to that kind of a design, of course, and one of the reasons some folks don't do it anymore. One solution is to throw hardware at it. If you can get to the point where you've got sufficient hardware that you can support symmetric active-active and really have equal performance across all nodes in your cluster because of the interconnects you have or the hardware you have in general, great. Unfortunately, in the price point we play at, we can't do that. We don't have the luxury of throwing hardware at it, especially, and as price pressures from commodity hardware solutions continue to push downward on our pricing, that becomes even more of a problem. So what we decided to do was stick with the Alua solution because we can't afford to do full symmetric active-active, and let's solve some of these issues. So for automatic load balancing, one of the things that we do is we actually rebalance ownership. Since we're in control of the ownership, we will rebalance them across the storage nodes based on the workload coming in. So we evaluate a whole series of different workload factors and make a decision on what's the optimal distribution. We do this by using connectivity data that we're tracking from, or the connectivity data that we are tracking related to the entire SAN. So what we do, in order to do the connectivity tracking, is we take protocol level connectivity information. So at the fiber channel, SAS, InfiniBand, iSCSI, whatever the other flavor of the week protocol we have to support. We understand where the actual physical connected paths are. We take that information along with some tracking of commands we see coming in on each initiator target nexus. And we say, okay, on each path from each host, let's keep track of the commands coming in. And we're going to look for evidence that the multipath driver on each of those has seen that given path before we call it usable. Because if the multipath driver on a given host has not observed a given path that may be connected, it still won't route I/O to it. So we have to be able to see that and understand that. And so we look for key indicators in the incoming command stream, like the presence of a report target port groups request, which is the SPC standard for reporting path states. And it says, okay, that's likely coming from a multipath driver. If they're querying our state, then we're in a situation where we think, yeah, we can see they're likely going to be able to route to this path because they were just in the process of discovering it. So we use this to understand, okay, given the connectivity of all the different initiators to the array at a physical layer, and then given the states we believe the multipath drivers in terms of how they discovered that, we can kind of get a feel for, well, okay, let's take a given logical unit. I want to move its workload from one controller to another. And if I want to do that, I have to ensure that all the hosts that have access to that given logical unit will be able to do so on the path I want to move it to. So we'll make those checks and say, yeah, we can move that over to the other controller to rebalance some of the workload. Everybody should be able to follow. Now, one of the things is that the standard also includes, the TPGS standard in SPC also has a nice effect of having a mechanism, because of the way we can report these path states. When a path state change, we can notify the initiators. The multipath drivers pick that up, see that the path states change, and they'll follow and route I/O over to the new optimized target ports, which lets us kind of drag the hosts around where we want them when we decide to rebalance workload. So this connectivity data is all key in making that work, all the tracking, all the inferences we're making about host connectivity and understanding of whether the multipath driver can route I/O to us based on the incoming command stream combined with the protocol level connectivity information. Now, as a side benefit of that, we have all that information. We can also report it to our users. We can say, okay, look, we think we see a connected path from this host to one of the controllers, but for some reason the multipath driver must not be seeing it because we're not seeing any incoming commands on that path that are indicative of the discovery process. So something's wrong with the multipath configuration. We can alert the users to things like that. So this is kind of a nice side benefit. So by moving to implicit Alua, we try to solve the ownership thrash issue in Alua. By using our automatic load balancing and a rebalance process, we try to solve the load distribution problem that Alua has. But one of the other big problems that ALUA has is when you change states, when you actually move ownership of a given logical unit from one controller or one storage node to another, there's a cost in that, and it's usually involved in terms of a latency spike. So our goal was to go in and minimize those latency spikes, try to reduce that to the point to the best as best possible. So we created an optimized ALUA state change process, or an ownership transfer process, that tries to minimize that by grouping logical units we want to move into a minimum number of transactions, but by intelligently grouping them. So for example, we might group them so that we don't put logical units that are backed by the exact same drives in the same transfer set. Because if you transfer those at the same time, remember when we transfer these, you have to flush the cache, any cache that you have, any unwritten data in cache that is, and get it out to the media before you hand over ownership, because it's the whole point of the ownership is the caching model. So you have a very lean caching model that doesn't require any kind of communication with the other controller in the fast I/O path. So we try to minimize the hit to the number of drives that are going to get hit during that flush process by making sure we group ones together from different that are backed by different drives, so we can do more parallel flush operations. The other thing we'll do is not combine things from different media types. If we've got a hybrid configuration with both SSDs and HDDs, you don't want to combine a transfer of a logical unit that's backed by HDD with the SSD, because the HDD is going to be much slower at flushing that cache out. You're going to have the SSD volumes in the group are going to flush the cache very quickly, and the HDD volumes are going to take a while, and then you're going to have the SSD volumes or the logical units actually sitting there waiting on the HDD volumes to complete. So we try to batch them by media type as well. We also try to immediately notify the initiators that the target port group states have changed, so that the ownership of the logical unit has changed, so they'll reroute I/O as quickly as possible. And we do that, and there's standard ways for reporting that to the unit attention. Now the other thing is that when we're transferring, it's one thing when you're transferring a volume ownership during a fault condition. Where there's been a connectivity issue in the SAN and something has moved because there's been a fault. The users have some expectation there's going to be a certain amount of a hiccup or a degradation, potentially a small latency spike while that happens. It's not, they don't like it, but it's much more accepted. However, when we're doing these for non-critical purposes, like rebalancing workload, where we're going to take an ALUA state change and move ownership of a given logical unit, that's something that anyone is willing to tolerate much of a latency spike on. So one of the things we do, besides trying to minimize the cost of doing the ALUA state transition, we also go in and try to make sure that we minimize the number of transfers we do. Our process of trying to rebalance workload will find the least transfer set. How many, I want to get to an optimal balance of workload between multiple nodes and multiple storage nodes, but I want to do so moving as few volumes as possible, as few logical units as possible. The other thing we do is we actually calculate a return on investment. Basically, we say, okay, how much is the workload going to change here? How much better is it going to get? Is it worth taking the hit of how many logical units we have to transfer? So there's kind of a computation that it says, this only improves workload balance by a small percentage, but yet we're going to have to move a whole bunch of logical units and incur a short-term latency spike on each. We can't have that. And so we just simply don't do that transfer, wait till a later time to see if we can reevaluate, because it's not worth it. There's just not a return on that investment of taking that latency spike to rebalance. Also, if the controllers themselves are just horribly underloaded, let's say each running at 5% utilization, because there's just a very light workload at the moment, it doesn't matter if they're even 100% imbalanced in terms of the total workload. It doesn't matter. There's just not enough workload there to worry about. There's no bottleneck created by the fact that the workload isn't balanced equally between the two controllers. So in that kind of case, we'll avoid doing any transfers. So in one case, we've tried to optimize the transfer process so that we minimize the latency spikes that are injected. And on the other hand, we try to avoid them to the extent possible and still achieve a workload balance and still achieve accessibility by all the hosts. So the other thing is recovery and failback. When a SAN connection or disconnect occurs such that some subset of the initiators lose access, we have this process where the ownership changes in order to follow where they can access it. We do that by tracking the amount of I/O that comes into a logical unit on each controller. And if one controller is receiving, that doesn't own it, is receiving a bulk of the I/O, we'll move the ownership around to rebalance to follow where the initiators are sending I/O. But then once the connectivity is restored, we'll recognize that because all the connectivity tracking we're doing, and then we'll fail it back because we want to put this back for workload distribution. We move things around in the storage node, between the storage nodes because of a fault. We've probably got workload imbalanced as a result. We want to put it back when it's done. And with the connectivity tracking data we've got and an understanding of whether the multipath drivers can follow a failback, we'll then fail back automatically. So this also allows us, because we understand workload balance, we understand all the connectivity from all the initiators, this allows us to sometimes not fail back. Maybe the connectivities come back, but conditions aren't optimal. But if you have a partial recovery, for example, and we might actually have partial connectivity restored to one of the controllers, but if we move things back, we'd limit bandwidth, for example. So with all this understanding of the connectivity, we can optimize and not fail back prematurely. So we have completely driven to the implicit ALUA model as a result. So for both a failover process, a failback process, and if we want to move things around for load balancing, it's entirely implicit ALUA driven. We actually tell the initiators in the initial discovery process, don't try to change asymmetric access states of the target ports. Don't move ownership. We're not going to let you do that. We're going to manage it. Fortunately, there's a mechanism in the standard for us to communicate that to the multipath drivers. So then this way we've solved the cluster thrash problem by totally managing it from the array. But it also means, because we're completely controlling all the ownership, balancing workload, that the system administrator, the storage administrator, does not need to worry about any of that. They don't have to worry about assigning ownership and rebalancing when the workload changes. They don't need to worry about the failovers and failbacks. We'll take care of all that as a process. So it's all really kind of the result of doing all this connectivity tracking that we're doing to try to, and taking advantage of all that to manage this logical unit distribution. So we get the advantage of ALUA in terms of the caching model that gives us a lean I/O path, but the storage administrator doesn't have to really be aware of that. So I'll go over briefly here. This test system is not a low latency kind of application. It's a high bandwidth application, but it is a large cluster. We sometimes in our media environments we work with, we'll see, in this case, StorNext parallel file system. So it's a multi-OS file system that is deployed on several hundred nodes in many cases, down to a single 2-controller storage array. So that's a lot of traffic potentially to a small system, but in those kind of environments, it's the number of nodes and the compute nodes in the cluster that lead to all the trouble with ALUA, because of the fact that we can have a risk for ownership thrash, because if they all make different decisions on where things should be owned. So that's why we moved to the implicit model. But what we're going to look at here is a test that was run with this solution. It's a high bandwidth environment. The key is that it's a large cluster. It has a lot of nodes. Now the test environment only had a handful of nodes, but we've deployed this after certifying this. We've then deployed this in a number of sites with hundreds of nodes, all connected to the same single two controller storage array. Now, fortunately, they don't all generate I/O at the same time. Obviously, several hundred initiators could easily outrun a small storage array, low-end storage array like that. But that's not typical of what we see. We see that we'll have a handful of initiators streaming a large amount of data simultaneously in that cluster. But the whole thing here is that we had to deal with these large clusters, and yet the fact that we're in a ALUA solution. So this isn't really an example of low latency, which is why we use the ALUA solution, but it's more of a demonstration of the fact that the larger cluster or a clustered solution can tolerate the ALUA, the implementation of ALUA. So, and I apologize, these are Dr. Gibby's slides, and so he conducted all the testing here, so hopefully I'll represent that fairly. So what we did was we performed tests to show the I/O throughput of the cluster as well as the resiliency of ALUA. And what he had was a pretty simple setup, just a handful of hosts through a switch and one of our E-Series controllers. So this is using the Alua model. And these are actually just a small number of drives, 24 SAS drives. So it's not a high performance kind of configuration, but it is a cluster that would be susceptible to this thrash problem and to many of the issues that Alua causes. So this particular environment where we tested this was a media environment, and we used an actual media test application. This is it's streaming video kind of application, and so there's the software typically used in that environment. The vendor for that software has a test suite that actually generates workloads that are typical of a streaming media kind of workload. So this is a case where we got folks doing video editing, video production, that kind of thing from these from this data. So that's the high bandwidth driver. So there's fiber channel interconnect, and we have those 3 hosts set up. They've got high-end, well, they're not real high-end, but they're video cards in them to generate the data. So this is actually running from application all the way down in the test that was run. So we installed our software in our newer firmware that has the Alua solution, and the implicit Alua solution, I should say, and set up the switches and configured StoreNext, which is the file system in use. And we ran certification. Autodesk is the provider of the software that some of these video houses use, and it's their test suite. So these are all streaming frame tests is what it comes down to. So there's it does rendering, it does real-time playback in these test suites. And so we've got clients running unthrottled 4K video. We got multiple 1080 HD streams, and there's various attributes of those video streams that I don't claim to understand the details of here because I wasn't involved, but the point is high bandwidth multi-node cluster. So what the results of that was that we were able to, we didn't have any cluster thrash. We were able to tolerate that with the Alua solution, which is what we were looking to try to verify, and we were able to actually achieve a max throughput with this, again, single node storage array, 24 SAS, nearline SAS drives. We were able to maintain a sustained throughput of 9.1 gigabytes per second. So that's reasonable bandwidth for a small storage, low-end storage array in this kind of environment. So, but that doesn't really talk about the latency piece of it, which is one of the pieces that we were trying to solve with the Alua solution as well. Now this is a test this is a small test with an 8-node cluster that we had run. And what we were specifically looking for here is what happens to the latency during these state transitions where we change ownership that's necessary with Alua to rebalance workload. And what happens during a failover and a failback, which also triggers the state transitions, for example. Now this was a nearline SAS drive configuration. I want to say there was only 12 or 24 drives in here, so it wasn't a very large configuration. So the ongoing latencies that we were generating were not exactly, amazing by any means. But the point here is what's the percentage spike in latency during these state transitions? And so what we see was that, for example, we saw latencies jump by several seconds when we had the solution that didn't have the optimized transfer process, the optimized Alua state transitions. And when we add them in, we saw anywhere from a 74 on failover. We saw a reduction of 74% on failback. We saw a reduction of 79% in the latency spike that occurs during those transitions. So kind of some validation that the general ideas that we applied to try to reduce those state transitions did indeed have an effect. This is just an example here of the reporting mechanism. I mentioned earlier that we have all this connectivity tracking data that we maintain. We might as well report it to the user if we see some fault in the SAN that we think they need to resolve. And so this is just a screenshot of one of the things we do to report to them. So it's kind of a side effect use of that data that we maintain. So kind of to go back and recap here, the challenges we had were that we want to use logical unit, or ALUA, so asymmetric logical unit access. We want to use a LUN ownership model in order to minimize the latency and the depth of our fast path IO path by using a very simplistic caching model that employs the ownership. So one controller handles all the IO, no communication with the caching between controllers. But the challenge is that we have this issue that ALUA creates in a cluster, which we also deal with, especially when you have different OSs on the compute nodes in that cluster. So again, the solution to that was implicit ALUA. One of the other challenges, the IO response time spikes during these state transitions. And of course, we talked about the way we batched the transfers, the way we optimized the transfers in order to minimize that total hit to latency. The balancing workload is also difficult in these cases, and so we produce this automatic load balancing mechanism that dynamically reassigns the LUN ownership and distribution between the two controllers to balance that so that the user doesn't have to manage that manually. And of course, manual management of that is a pain for the user, manual management of the distribution of LUN ownership between the two controllers. And so we use this connectivity tracking data and report on it to the user when there's faults. And we also use that to do our automatic load balancing analysis, our failover failback, so that we handle the ownership completely. The user doesn't have to concern themselves with it. So just some conclusions. We can continue to improve this kind of interoperability, continue to do work in this area and research, trying to figure out ways to better support these clusters and better meet the latency requirements with the same firmware, with the same storage solutions. And the testing that we did demonstrated that we can actually do that in a clustered solution without any issues, in a high bandwidth clustered solution. And some of the testing we did also shows that we minimized the latency hit during the ownership transfers. And we continue to evolve this as we move forward. But the big thing I want to impress here is that the move to implicit ALUA is really what allowed us to do that. It wasn't the optimizations are all key part of it, all making ALUA easier for the user. But the fact that we moved to implicit ALUA is what solves a lot of the nastiest problem with ALUA, and that's the ownership thrash in a clustered environment by letting the array manage the entire ownership of all the LUNs. And that's all I've got, so short and sweet. Any questions? Yeah.
I've got about 60 or 70 questions.
Okay.
Let me refrain.
Relevant to this?
So, are you flipping the affinity at the LUN level or the storage pool level?
At the LUN level.
At the LUN level?
Yes.
Okay.
Now, one of the things we do is we try to avoid having logical units backed by the same drives owned by two different controllers if they're HDDs. Because we don't want head thrash. If we got two controllers flushing data out to the same drive set and they're not, we can do an elevator sort to actually flush by LBA on HDD within a controller, but when you split that across two and you're hitting the same drives, you're going to get more head thrash. So one of the things we do is we minimize to the extent possible. Again, there can be connectivity situations that you're forced us to move ownership to a certain controller, but in an optimal condition, we try to keep the ownership of a given set of volumes or LUNs backed by a certain set of drives to one controller to minimize that. If it's HDD, if it's SSD, we don't care because there's no head thrash issue, right?
Okay. And with the older versions of ONTAP, you were running two storage nodes and you were assigning affinity to node 0 or node 1. But on the newer versions, you can run a global namespace across like a 4-way cluster array. Will this load balance across 4-way cluster array?
So this is
ONTAP?
This is actually the NetApp E-Series product, which does not run ONTAP. This is a pure SAN block solution, so it is not ONTAP. The concepts will apply to a multi-node cluster. We are just a single 2-node HA pair, kind of a pretty typical low-end configuration, right? But the same concepts could be used to scale out across multiples, which is one of the things that, as we worked with this and tried to employ the design, we wanted to make sure that it would scale out if we decide to do a scale-out kind of solution.
Also, the competitive products in the marketplace, are allowing the storage administrator who configures the box
Yep.
to assign affinity to either controller 0, controller 1, or whatever.
Yep.
You still get automatic failover and redrive the
Right.
I/O.
So we do the
You
same.
don't get automatic switching at the storage subsystem level, which is what you're proposing here, correct?
Right. I mean, so we do allow manual assignment if because the assignment is really about balancing workload, right? And so if the user decides that, for example, or one thing they may decide, you know what, I can't take the latency spikes that these periodic rebalances of automatic rebalances might cause me, I'm going to turn that off. So they can turn that off and they can manually assign the affinity to a given set of controllers for a given set of logical units, and it will stay there. It will still auto fail over and fail back using the same mechanisms here if we see connectivity faults. So we're still doing the same connectivity tracking even if that's turned off, right? If the load balancing is turned off, and we can still fail over and fail back. So you can operate in either mode. You can either have it, in some situations that aren't as latency sensitive, the user isn't as savvy about balancing workload, then the automatic mode seems, fits best. But in the case where they don't, where they do have a very deliberate configuration, highly tuned kind of thing, and they are aware of what they're doing with respect to balancing workload, balancing ownership, then we let them do that. So all of the tracking, all of the failover, the failback, all still works. It just doesn't do the periodic automatic evaluation of the workload.
I have one final question, which was a couple of years ago as an industry, we on the storage subsystem design and manufacturing side got together, all the vendors, and decided we were tired of maintaining load balancing and path redriving at the device driver level.
Right.
So we had products like PowerPath from EMC, and we had SDD from IBM and others. And we went to the OS guys and said, hey, how about putting load balancing and path redriving into the OS level, and we won't have to then certify all these device drivers with every little dot release of your OSs. So that happened, and that's the way the industry looks today. The load balancing path redrive or in the OSs. So my question is, have you tested, how does this interact with that path redrive and load balancing when you also now layer on top the controller?
The storage array doing the balancing, yeah.
At the subsystem level.
And so what we're measuring, we actually measure the workloads as it arrives at the target ports on the controllers. So if there's rebalances, and we're periodically evaluating that, right? So if there's rebalances that happen at a higher layer in one of the hosts, or all of the hosts potentially, because they're observing latency on given paths and making decisions about routing. If they're doing, in other words, if they're doing more intelligent routing than just say round robin or most recently used kind of path routing algorithm, then that will drive changes to the counts that we're obtaining. We're actually, observing counts on each target port and tracking all of that. And so we will see that dynamic change in our workload, and we react to that. So when we do our evaluation, we will essentially auto-tune ourselves to what those initiators are doing. Is there the potential for it to actually go in and the two kind of compete in some ways? Potentially, yeah. But it also learns. We have thrash avoidance mechanisms. If we won't move a LUN here, then back here, then back here, then back, we will have mechanisms that dampen that to ensure that that doesn't happen.
And I guess the final point is, I'm assuming behind the controllers, you have access to a continual common raw disk pool.
Yes.
Yeah.
Yes. Yeah. Dual port drives, right? So common connected from both
With
controllers.
SAS connectivity coming up from the
Yes,
top.
and redundant crossovers on the SAS network and whatnot. So now, and what we're also trying, looking towards, NVMe on both ends, both NVMe drives and NVMe over fabrics on the front end. Same kind of connectivity. Most of the same concepts can be applied. Different protocol, but most of what we've done is at a generic layer that we can apply that as well. The network, the fabric on the back end to connect to the drives is a little different, and obviously the protocol is different on the front end, but same concepts in general. So as we look forward, we're hoping to extend that same concept forward to different generations of new protocols.
I think it's very valuable. My compliments.
Thank you. There was another question back here just a minute ago. I don't know what. Okay. Any other questions? Yes.
So you said, sorry, I came in a little late. You said you look at at least the OS that you're seeing.
Yes.
On the other side of the IP nexus.
Based on what the storage administrator tells us that is. So they map a port worldwide name to an initiator, and then we give us an OS version of the initiator to help us kind of tune our behavior,
Yeah.
right? Because
Can you use that to avoid like stupid behavior or multi-tapping?
to,
Maybe in like, one OS versus another?
yeah, I mean, essentially what we do is we use that to tune well, this particular multipath driver will behave this way if we return this check condition, or it'll do this bad thing if we return this check condition. So don't return that check condition, to return this one instead. I mean, it's tuning that we don't like to have to do, because in theory, the whole thing should be standards based and everybody should work identically, but we all know it doesn't work that way. And so, but one of the things we have seen as we've moved more to the implicit ALUA model, and as the standards, develop the TVGS semantics for path reporting and everything, a number of 10, maybe 12, maybe it's been 15 years ago now, I don't remember, that we saw a lot of improvement in the consistency. It's not all a bunch of vendor unique methods anymore. The drivers behave pretty consistently. They adhere, for the most part, to the standards. So it's minor differences now, as opposed to where it was 15 years ago, where it was major differences in the way you interoperated with the different HBAs and OSs, because all the solutions were unique. Where now it's a little more standards-based, and that's actually allowed us to do this as well. If the multipath drivers did not react well to us making an ALUA state change and all religiously follow us over to the other new optimized target ports, we couldn't drag them around and rebalance workload, right? So we're taking advantage of the fact that there has been some standardization in behavior among the various drivers, and for the most part, all the major OSs behave quite well. We don't have near the difficulties we did some time ago with this. I don't think we could have done this 15 years ago.
I assume that you watched the changes in post-multipath software to be sure that you're not doing the wrong thing.
We do both that and we test it. Interoperability testing is a key here, right? Because it takes a lot of that. And to your point earlier, right, it does take a lot of certification. For the good or bad of it, we have to do that anyhow, right? We have to do that to certify given HBA combinations and drivers and OS versions and all that, because there's more than just the multipathing that can bite you here. So, that certification has to happen. And so we've got our interop group trained to look for those kinds of, hey, wait a minute, the multipath driver's behaving differently all of a sudden. What happened here, and we can kind of pay attention to what's going on. So we've, for the good or bad of it, had to become experts in what all the OSs are doing. Anything else?
I'll just make one more point, which is one of the nice features of this, if you can get it into your product lines, on a broad scale. It's one less thing for the storage admin to worry about.
Right.
Because every time there's a performance problem, one of the things you get concerned about is tool affinity on a controller, because most of the competitive products, including many of your other products in enterprise, the admin has to worry about putting this pool on, I'm giving it affinity to this controller, I'm giving that one affinity over. And that's been a consistent, storage admin headache over the years.
Yeah,
So it's a really nice idea.
Thank you. That's one of the things we've tried with this automatic load balancing. It's difficult to do because there are so many possible combinations. Figuring out, searching such a large space for the optimal configuration is not trivial. And then also just the fact that you're kind of always chasing your tail there, because you're watching the incoming workload, seeing where it needs to be rebalanced, and when you rebalance it actually has an effect on the system such that it changes itself, and it's not an easy thing to do, but it's better than the storage administrator sitting there making that guess on their own.
What's the logical unit granularity that where you're coming to a decision point?
It's
in the data?
It's individual logical units.
Individual what?
Individual logical units. But like I said earlier, we do kind of we are cognizant of the drives that then back those logical units to ensure that we don't do something stupid there with respect to causing head thrash on HDDs and that kind of thing. But it is actually, we will select individual logical units. So if you got all your workload coming to one logical unit, yeah, I can't do anything about that.
Are you looking at factors like just I/O operate and data rate, or are you looking at connect time, or how deep are you getting in the?
It's
what's the decision trigger?
IOPS bandwidth, both an IOPS and bandwidth consideration. Write cache utilization is another. If we've got a lot of heavy write load on some LUNs, that might essentially saturate our write cache on one controller. We might choose to move that to the other. We've got back-end considerations. So after you go through RAID and you end up on the drives, what's the balance of workload across the drives on the back-end channels between the two controllers? So we got both front-end and back-end balance considerations calculated in, and then we have to also balance against that cost I was mentioning earlier, which is try to minimize the number of LUNs you move, try to end up in an optimal distribution that minimize the thrash, don't let these things bounce around. So all these factors come into play in making that load balance decision.
It can be really helpful for backups, because one of the problems with backups is the controllers have limited amounts of NVRAM that you can put,
Yeah.
To commit writes when you got a sustained sequential data stream coming in.
Right.
And the dirty data that's in the NVRAM has to be destaged to the back end. And when that reaches maximum, the entire subsystem then becomes gated.
Right.
And if you could flip the affinity for those sequential writes to an alternate controller,
Or balance in between. Yeah,
has
right.
open NVRAM available,
Right.
that'd be really helpful in backup stream.
And that's essentially what, by watching the number of writes coming in, we can, and the write cache utilization, we actually track the number of blocks utilized in the write cache. So essentially, if you get a large sequential stream like that, it'll calculate that as a heavier workload on the cache on one controller than the other.
Very nice job.
Thank you. Anything else? All right, we're out of time. Thank you.